Okay, let's get started. Second session. So these water molecules are basically this whole property of water, including this liquid water, are coming from the nature of the hydrogen bond. So each individual water molecules are held together through hydrogen bond like this, and the reason why water is as a liquid is each of these hydrogen bond formed water molecules are constantly being broken at the moment, and some other areas are like reformed, so it does not stay static, but it's very dynamically broken and reforming types is being repeated. So this flexible shape is because of this that is being shown due to this constantly broken at random spot and also constantly formed at the other spots of these water molecules made this. So it can be contained in a bottle, and any shape of water as a liquid can be made into it. And also ice. Ice is a solid state of the water also being maintained through hydrogen bond of each water molecules. However, in this occasion, their dimension is when it's in an ice state, then each individual hydrogen bonds are every possible maximum hydrogen bonds are being formed at each different water molecule. So they have certain wide dimension, whereas in liquid form of water, because of this being constantly broken and reformed property, they can take up much less. The same number of water molecule can be put into much smaller space. In other words, the density-wise, density is always defined as the number of molecules in a given space is the density. So density of water is kind of counterintuitive in that usually you consider that a solid is denser than the liquid. That is the case for most other substances, but in the case of water, liquid water is much denser than the solid water, which is ice. And the significance of such thing is this. So ice, during the winter in the temperate climate, when ice formed on the surface of water, like on a pond and on the river, ice will float because of this less dense property. So it spares the life forms underneath. Otherwise, every winter we have to do this recreation of this whole life forms, because ice will start formed at the bottom, then everybody will die during the winter, and when spring comes, then you have to recreate all those the living things. But thanks to this water property, so underneath of water, still life forms can hide and sustain themselves until the better times come, until the spring. So that's actually a very significant contribution of the maintaining life. This particular property of this water is as such. And other unique property of water also come from this very hydrogen bond property, including cohesion, adhesion, and surface tension. What's the difference between cohesion and adhesion? I found a very intuitive cartoon explaining the difference between cohesion and adhesion is this. Two water molecules, when they try to hold together, this is through cohesion. So water molecules are basically, they are sticky they tend to stick together. And that's what we describe as the cohesion property. And adhesion is water itself is also sticky to other surfaces. So when this water molecule try to wet other surfaces, then we call that as an adhesion property. So that's the difference between adhesion and cohesion of water. So yeah, I found this secret under the Google search. So probably so can you when try to type in cohesion and adhesion. Probably you can also find this very witty cartoon about explaining the cohesion and adhesion. And also because of that, because of this adhesion property, water will try to climb up because of this adhesion to wet the surface. Unlike mercury, when you try to read the temperature of the mercury, that you usually tend to notice this the level, liquid level, will have this shape as opposed to this particular shape of water. And this has the biological significance in that it's like trees. When you have a high tree, they have to be able to draw water from soil, then they have to be able to bring this water to very high top. And this turned out to be very important property of water, together with other property of water, like including cohesion, as well as some other tricks that plant also have to play. So in combination of all this cohesion, adhesion, and plus something else, we call it transpiration, that we don't have to worry about. So that's how this water in the ground can be brought up to this way. Some trees can be as high as like 10 meter or even 20 meter. If you try to think about it, how would that be possible to bring this water to the way all the way up to like 20 meters up? And this little property of water is the things that making possible this travel, whatever. And even voila, there's little I forgot the exact name of this insect. Some insect can like behave as Jesus Christ, so that they can walk on the water like this. And because of this, the surface tension will so-called, because water molecules tend to gather themselves to. It's all about it's like entropy actually. So because of that, when you try to push some pressure on the surface, they have a strong resistance against it, and that's how it showcase this type of being able to float on the water and then walk. Wow. So anyway, with all those important and unique property, water became the very essential molecule for life. And not to mention that actually all those life forms originally began in the water. That's why. So this is the exact the statement, comment written on your textbook. Like life as we know actually originated in the water. So in other words, all those different life characteristics are the result of this adaptation to this particular unique property of water. So this something that textbook stated about this particular interaction relationship between water and the life that trying to adjust to its property. So it's the result of all this present days of life form is the result of this particular specific adaptation of this environment, watery environment. Okay. So another important area where we consider this hydrogen bond such an important factor is maintaining this DNA structure. DNA long strands usually exist in double-stranded. And the reason why DNA exists in double paired strand is due to this hydrogen bond. Individual components of DNA actually are held together through hydrogen bond that we are going to take a look at shortly in this chapter too. And so if I actually put this hydrogen bond as a very intuitively, it's one punchline property is just like a Velcro-like property. Individually, hydrogen bond is very weak in strength. However, they usually tend to exert its force in mass. So if you think about this, the force of this Velcro, each individual unit of Velcro is very weak. However, altogether, the Velcro provide very, very reliable, strong bond. And so is this hydrogen bond too. And usually that's why hydrogen bonds are being played in altogether in mass. And together, it is a very, very unnegligible force, a very strong force, although individually it is very weak. So in DNA structure, the orange line indicate the hydrogen bond. Not only that, protein themselves, in maintaining the protein structure, hydrogen bond is another very important factor. And also, when a protein tries to interact with a certain area of DNA, and that is a very important mechanism by which certain genes are regulated in its expression. Probably some of you are I don't know what you are talking about, gene expression, whatever. Later we will get to that. When try to control the gene expression, usually we need this force of the protein on particular area of the DNA, and all these are actually dependent upon this hydrogen bond. Yeah. So individual strength of a hydrogen bond is very weak. However, altogether it provides very, very stable and reliable force, just like this Velcro type of things. And also hydrogen, not only that, the hydrogen itself, we are talking about only hydrogen element, ion, is the very important determinant of acidity of solution. Actually, whether a certain solution is acidic or like alkaline is mainly determined by how many hydrogen ions are there present in a solution. So this, like being acidic or being basic, alkaline, is simply solely determined by hydrogen ion content in the solution. So like strong acid, when we think of the strong acid, the reason why some chemicals act as a very strong, nasty acid is because when they were put into the solution, that chemical will immediately generate hydrogen ion into the solution. So because of that, the amount of hydrogen ion in the solution rapidly increase. Then we, by definition, call such chemical as a very strong acid. For example, like the very famous strong acid, which is hydrochloric acid. When this hydrochloric acid, the chemical, was dissolved into the water, immediately what's happening is immediately like these two ionized. Hydrogen ion plus chloride ion, they get dissociated into this in the water. And this is so rapid, and almost all of this hydrogen become ionized. Then we call them as such a strong acid. On the other hand, a weaker acid like a vinegar, and they have much less tendency to do this ionization. So when the same amount of vinegar comparable to this hydrochloric acid were poured into the water, the amount of hydrogen ion that being generated by this is much less than the case of hydrochloric acid, and that's why we consider vinegar as a weaker acid. So that's the difference between strong and weak acid. And a lot of times, actually, biological system has to worry about the particular acidity or alkaline property of a condition, because a lot of important material working in the system is heavily dependent, very sensitive to particular condition of this acidic or alkaline. For example, very good example is protein is one such a component which is very sensitive to the acidity. If they have some kind of beyond a certain level of this defined acidic or alkaline condition, and a lot of protein structures are not maintained properly, so their function, they cannot work properly. So that's why we have to worry about this particular condition of, and usually biological systems try to maintain this condition as a neutral, sort of neutral thing. However, in some occasions, like think of this, our internal environment of our stomach, which we deliberately maintain as very acidic for some reason. And in the cell, there is a very similar area inside of a cell. We are going to get to that later. So each the particular area or compartment, we do maintain some very specific condition of this acidic or alkaline solution, for that matter. That's why. And usually those acidity or the alkaline property is indicated by something we call the pH. If you know what pH is, okay, good. But if you just didn't know yet, no problem. pH is nothing but this particular negative log of hydrogen ion concentration, whatever it is. Okay, so if you put this as some kind of number of hydrogen concentration, then you get to have some type of a specific number, and that's what it is, like pH. So here, usually hydrogen ion concentration of pure water is 10 to the minus 7. So if you plug this 10 to the minus 7 onto this formula, then you get pH is 7 over here. That's why pH 7 is some kind of neutral, kind of a standard for neutral. So if you have a more hydrogen ion concentration, then this number, because this logarithm is a negative, minus. So if you have a more concentration, and the number will get less and less. That's why acidic pH is something like under below 7, and alkaline pH will become above 7. That is the reason. So like some of the familiar component material substance that are highly acidic actually, and some others are highly basic or alkaline. That's it. So that's so much about the hydrogen bond that I can think of. So that's all. And still a lot of those things that I put out today, you don't really need to remember or anything to carry on. Simply, basically, as long as you understand what's the basic principle of a hydrogen bond and why these hydrogen bonds are so important in biological system, that will be simply just it. Other detail, miscellaneous details, who cares? Now, let's talk about another very weak chemical bond. Its name is also weird. It pronounced van der Waals force. This van der Waals force is very mysterious chemical bond in that obviously there's a kind of attraction between two molecules or two elements in either case. But this van der Waals force is not something like a more stable like hydrogen bond or ionic bond or covalent bond, not to mention even, but it is extremely like temporary, tentative or momentary incidence reaction. When two molecule or two elements approaches together into very, very, very close distance, and somehow between these two substances, some attraction is generated. Why? Because in each of these two elements or molecule, whatever, they have these circling electrons. Electrons move around, and depending on that particular position of an electron, randomly speaking, and they generate some kind of attraction between probably what is that guy talking about? Let's consider this. Two substance. It could be two elements or whatever. Electrons move around. And it is always like this electron movement is such a random activity. So we can imagine at some point the electron on this left side substance somehow gets too close to this surface. So partially delta minus partial charge because of the presence of the electrons over here at this point. But you can also think of, on the other hand, this molecule or this element, electrons moves away from the other opposite area. So this area becomes partially positively charged. This instance can happen, yes. And also you can imagine when under this scenario, attraction will be established. In the case of a hydrogen bond, you have seen this thing. So this is much weaker and more subtle, but still it is something really in existence. It exists. It's there. It's not something like imaginary, like bogus, hoax, but it is real. This van der Waals, although we don't usually recognize that as, but it is there, and it happens. And it actually plays a very important role, especially in biology. So much as the hydrogen bond or ionic bond, this van der Waals force is another very important driving force maintaining life intact. So when these two elements are away, this far distance, no van der Waals force will be possible. But when they approach a certain very, very close distance, then obviously there will be some van der Waals interaction will occur. But on the other hand, when these two molecules or element gets to be much closer than that, and hey, don't get me closer than that. I don't like it. It's always a natural reaction, whether it's between human or in between molecules. So this, on the other hand, because instead of attraction, there will be some kind of repulsion occur. Okay. So, in other words, van der Waals force always has to be in the very, very correct, some very accurate distance between these two parties, whether they are molecules or whether they are elements. And then it happens. So, because of that, between these two parties, if, like, let's say, these two area which is like wider like this, and there is a higher chance of having more stable van der Waals force is possible over there. But if these two pointed molecules try to approach together, because the contact area is much less, so the strength of van der Waals force is much weaker. So in the case of a van der Waals force, this area, the surface area, is important, wider. Another thing is this surface area. If these two surface areas are somehow complementary, what I mean by that? If this is one example of the complementary area. So one area can have some enclosure on the other side, complementary, instead of if these two surfaces then these are not complementary. So complementary surface is another very important factor to have stronger van der Waals force. So here, this is an example to showcase such an importance of a complementary surface here. Exactly same number of carbon organic compound, but depending on how their surfaces are arranged, then you can measure actually the strength of a van der Waals force by their different boiling point. The higher their boiling point, that means it's much more difficult to break them apart. That means there's a stronger van der Waals force is there. And the only difference among these three organic compounds is they do have the same number of carbon and hydrogen, but simply their interacting surface areas are different. So that's kind of a support, proof that in making up the van der Waals force, this surface area, especially if those two surfaces are complementary, that's the better. So once again, this van der Waals force is very weak, even weaker than the hydrogen bond, but their biological significance is probably more so than the hydrogen bond, I think. Like, for example, this important interaction between antibody and antigen in this particular era of pandemics, everybody is so concerned about the strength of antibody, right? But this, in general, interaction between antigen and antibody is maintained mainly by van der Waals force. So those two surfaces are complementary. Some particular surface of these antigen, like a coronavirus surface, and antibodies, like recognition surface, they have this complementary shape, and then they click and then grab it. And this grabbing force is mainly by van der Waals force. And more importantly, enzyme to perform the chemical reaction with particular specific substrate of a given enzyme is all these interactions are mainly, although I'm not saying the enzyme substrate interaction is always only through van der Waals force. No, some other forces like including hydrogen bond and ionic bond also are there to participate, but mainly you will be surprised that actually how much of this van der Waals force is there to establish this particular interaction. And also receptor ligand. The particular interacting component against some particular receptor is called ligand. Okay, I'm going to go over this ligand and receptor interaction later on. So right now, you don't really, if you are too much like putting in today, simply forget about it. But anyway, all these biologically important activities are actually, without this van der Waals force, would have been impossible, is what it says. So this is a modeling, structural modeling showing interaction between antibody and antigen, whichever is whatever is not important. And in this actually particular example of modeling is last year, scientists actually determined particular interaction between this antibody and the coronavirus surface, and this is exactly the case of interaction between the coronavirus antibody and its particular the surface protein of corona. It's all based upon this such van der Waals force. And even weird example of this particular lizard, its name happens to be a gecko lizard. This gecko lizard is very important in that it shows such a marvelous ability of climbing up at the right angle of surface, glass surface, without any aid. So it is something strictly straightforward wall, it can climb up so easily. And it turns out that it's all due to their very unique shape, structure of the bottom of the surface area of their foot. And if we zoom in, their surface area has a very, very extended surface area to easily create such interaction, van der Waals force generating interaction with the surface of a glass wall, and it generates some of the very sticky force, so that's how it can climb up. So that's about the van der Waals force. Anything else? Yes, there is another. Hydrophobic interaction. In some general biology class, it's been described as a hydrophobic bond also, but it is not actually truly a chemical bond. Hydrophobic interaction itself is not something that chemical bond in that, because it does not provide any maintenance. It is a phenomenon, hydrophobic interaction. So let me give you some distinction, but just bear with me. In the watery environment, we call this the professional terminology. This watery environment we call as aqueous environment, as opposed to organic environment, like a oily environment. But this purely water-based liquid environment we call as aqueous environment. So when all this material matrix is water, then imagine you are individual component dissolved in, or have to dissolve in the water. And what kind of a chemical property you have actually determines your fate. If you are lucky enough to become like you are either this or that. Hydrophilic or hydrophobic. Hydrophobic means water hating or water avoiding. Hydrophilic or water loving means. So depending on your polarity, especially on your surface, like depending on your chemical property, either you are hydrophilic, so you have no problem with associating, make friends with water. Let's say these are individual water molecules, right? Individual water molecules are all polar, right? So if you are somehow lucky enough to have some kind of polar surface, then you are hydrophilic because of this polarity of your nature, chemical nature. Then you wouldn't have any problem of having intimate interaction or association with water molecule. So you will be easily dissolved in the water. You have no problem. But not everyone is so lucky. Some molecules are hydrophobic. What kind of molecule could that be hydrophobic? Same principle. If you are polar, then you will automatically become hydrophilic. So in other words, if you are non-polar, which is a very good indication in that you have one carbon and two oxygen. So because of this oxygen, you have a partial charge. Oxygen is always electronegative, so become polar. But here you have one carbon and four hydrogen, right? So it's a non-polar. You don't have any area to generate any kind of a partial charge over here. No one is so greedy about electron in this particular molecule. So you become non-polar molecule. Then you would have a very difficulty in dealing with water molecule. Because of this, water is polar and you are non-polar, so there will be some kind of a tension, repel each other. So how are you going to survive here? You have a really, really big problem of surviving in this hostile environment, hostile watery environment, the only way you can survive here is stick together. So that, because you are basically water hating. So your property is you try to avoid making any contact with the water as much as possible. How can you do so? By gathering yourself together. So, hey, everybody come up, huddle up. Hydrophobic, every one of you hydrophobic molecule huddle up, and let's have some kind of a scrum, and so that you can reduce any potential contact with water. That's one way of survival. As long as you can reduce the surface area making contact with water, you will be okay. It's all governed by the law of thermodynamics, which is the entropy. So that is the most stable shape condition, so that you can have the highest amount of entropy. Ironically speaking, it may sound. So anyway, so all those hydrophobic molecules will have this kind of sticking together, aggregating in the water molecule. Instead, hydrophilic molecule will easily, freely dissolve. When you say something is dissolved, that means they are covered up. Each of the surfaces is covered with water. That's how we describe it. They are dissolved. They are not going to be dissolved because of this, so they will stick together and have some kind of clumping. And this force, this tendency of clumping together in the water environment is what we call hydrophobic interaction. These hydrophobic molecules will tend to clump together. And how do we describe? That's what they are doing. So they try to stick together in the water is what we call hydrophobic interaction. But in itself, it is not any kind of a chemical bond, because there is no strength or force being generated. But it is a simple kind of tendency, but it can stay there. It can stay there as long as, if they are lucky enough to generate here between these surfaces, what? Guess what? What kind of possible chemical bond that we have learned today possibly provide some of the more stable maintenance among these molecules? Ionic? No, because they are not ion. Covalent? No way. Hydrogen? No, there's no hydrogen bond possibly can occur. Then what else? The only possible, van der Waals, yes. Of course, especially if they can somehow generate some complementary surface among their interacting area. Now van der Waals force, because van der Waals force is everywhere. Anybody can have a van der Waals force. Unlike ionic bond can only be formed between two ions. This doesn't count. Hydrogen bond can only be formed like on a certain condition of hydrogen in a certain condition, so it doesn't count. Covalent bond, on the other, no way, there's no way. But van der Waals force does not discriminate. Anytime two molecules are closed together and have some kind of a decent shape to generate complementary surface area, then van der Waals force will occur. And actually, the van der Waals force is the one maintained once they are together. The reason why these hydrophobic molecules are put together is because of this hydrophobic interaction, right? We admit. That's the thing. That's the start. However, to keep these hydrophobic molecules together, what we need is a van der Waals force. That's the subtle difference. So, this is another very good diagram I found on the internet by Googling. So hydrogen bond in the watery environment, and let's say these two molecules are big fat molecule like hydrophobic molecule, and they will aggregate together due to this hydrophobic interaction. However, this surface area, okay, along with this surface area, the van der Waals force is formed, and that's the reason why they are kept together. That's what it says, okay? So actually, this important determinant for protein structure is because when protein is being generated, when the protein is being freshly made, this whole entire protein is like its shape is not determined yet, but usually it's a whole entire big protein. It has some hydrophilic surface as well as some areas hydrophobic surface due to their structure. And what's happening is this protein synthesis is being made in the watery environment. That means, let's say this big belly is a hydrophobic area. So immediately when the protein is being formed, this big belly area, which is hydrophobic, will do this. Yeah, it will fold to reduce due to this hydrophobic interaction. And that's the beginning. That's the first step of a correct protein shape formation. So that's why protein structure formation is actually mainly, hydrophobic interaction is very important in protein structural formation. So like here in some of the hydrophobic area, otherwise this hydrophobic area will be covered with the water, which is not good. When this hydrophobic area form, they just get together, clump together. Now we are talking about correct protein shape. And this is done automatically, spontaneously. We don't have to do anything. Usually, no enzyme is required because it will be totally governed by the law of physics, like same entropy rule. Okay, so, and another thing is a lot of those diseases are actually result of this misfolded protein misfolded thing, and the common denominator, common characteristic of those unfortunate diseases are proteins, normal functioning proteins we found in those patients. They are clumped together. They show this protein aggregate. See, like in the case of Alzheimer's and in the case of Parkinson's, and also like minor end of this disease. I shouldn't say this is minor disease. Another very well-known example of a so-called sickle cell anemia. Those all three cases actually the same protein aggregates are the one actually responsible for those diseases. And this program is showing that the sickle cell anemia red blood cell, normal red blood cells are like this, like cushion or unfinished donut shape, nice shape. However, this malfunctioning red blood cell, we call it the sickle cell red blood cell. What's wrong with this sickle cell red blood cell is the inside of this red blood cell. When you have this mature red blood cell, all you have inside of a red blood cell is one particular type of protein, which is hemoglobin. Because hemoglobin protein is the one which functions as a carrying the oxygen. And mature red blood cell, the cell dump everything else. They don't need anything, but only highly accumulated this hemoglobin protein to better fulfill its function. All my duty and function is simply to carry out this oxygen delivery. That's all. Fine. However, the structure of the hemoglobin protein has some kind of malfunction, deformed structure, then you have a problem. So this is like kind of normal hemoglobin protein structure, say. But what's happening is there is a mutation, genetic mutation, to prevent some proper protein folding. So let's say this area, this stuck out area represents the hydrophobic area. Normally this stuck out area should be buried inside, just like this area. It goes like this, but due to this genetic mutation, this hydrophobic area is placed on the surface of this hemoglobin protein. That's what happens. And then problem is, this hydrophobic area cannot stay stable on the surface of this watery environment. So to prevent that, what do you have to do? They stick together like this. All this hydrophobic area were buried, hidden to cover up them. It's just like this protein is simply practicing the rule, natural rule of hydrophobic interaction. That's all. It's their fault, the gene's fault. Why did you have to do this mutation in the first place? But anyway, as a consequence, you do have this, and as a consequence, you have this aggregation. Normal hemoglobin will individually perform its function as a solo. But when you have this long, huge pile, then this protein will settle at the bottom of your cell, not being able to do any function. And those sickle cell, red blood cell, is a result of this accumulated, malfunctioning, aggregated hemoglobin protein. Then, obviously not being able to carry out any oxygen transport. In this previous photograph, you do have a mixture of normal red blood cell as well as the sickle cell red blood cell. You are lucky. However, if your genes, if you carry this both of your chromosome, this mutation, then you're not going to be able to be lucky like this. All of your red blood cells will become like this sickle cell. Then you are in big trouble. So, but the point is, here I'm not going to talk about the nature of disease, but this hydrophobic interaction and as this kind of a consequence of a genetic mutation which lead to different malfunctioning, incorrect protein shape, protein folding is the main actual cause for many important and disturbing disease like sickle cell anemia, and also same thing for Parkinson's and even diabetes and for Alzheimer's are all actually same basic principle of this incorrect protein structure. Okay. So with that, we have finished all this chemical bond. Easy, that was it. Yeah. So everything. So all those things that you need to worry about. Being able to distinguish which one is different. And one final word about those chemical bond is, once again, let me emphasize the importance of a weak chemical bond in biology. Like, for example, consider if enzyme, like the one as a very useful tool, machine of maintaining this all different chemical reaction inside of our system to maintain the metabolism. If somehow this enzyme's function in combining with the substrate and then doing this chemical reaction was solely dependent upon covalent bond, what do you think? What might have happened? If in these days, like nowadays, the fact is enzymes, this interaction with substrate is mainly dependent upon the weak chemical bond such as van der Waals, hydrogen, and ionic bond. Right? Those three are the main chemical bonds making possible that enzyme-substrate interaction, for example. However, instead, forget about those weak chemical bond. I don't like those weak chemical bond. I want some more stable, strong chemical bond. So how about having covalent bond based enzyme substrate interaction? What do you think? Would it work? Yes or no? No? Or maybe yeah. Oh, that's the correct answer, because if that worked, then probably we would have seen already those enzyme and substrate interaction based upon covalent, but we don't see such a thing. All those enzyme and substrate interactions are solely based upon such a weak chemical interaction like van der Waals, ionic, or hydrogen. Why? So yeah, let's imagine the other opposite scenario where covalent bond is the one governing this enzyme substrate interaction. Then what would you expect? For example, speed. For enzyme, speed is the key. Enzyme should be able to perform its chemical reaction very, very, very quickly. Like we actually label differences like different enzyme by solely their speed. And if they are quick in generating those finishing chemical reaction, then we consider those enzymes as a very good enzyme. And if some enzymes are very, very slow in finishing up this chemical reaction, then we despise them as a very poor second grade, third grade enzyme. So in this case, covalent bond, it might give a very stable interaction. Covalent bond is a very strong, stable bond. So why not? Why not we just create some covalent interaction between enzyme and substrate? It's going to be very stable, strong. So wouldn't it more reliable? Maybe, but on the other hand, such reaction would be much, much, much more difficult to take this away, to destroy. So probably if we decide to depend on the covalent bond in establishing this interaction between enzyme and substrate, it would take probably forever to finish one reaction. So everyone wouldn't exist here. So that's the one main issue. Why such a weak chemical interactions played such an important role in many, many, many different biology, including enzyme reaction and also antibody antigen reaction and some ligand and the receptor things should be temporary enough, instant temporary, so that we can quickly change the things depending on different circumstances. But this covalent bond cannot keep up with such quick reaction. On the other hand, covalent bond has other area. Covalent bond is so strong and unstable so that it is really ideal to build such huge macromolecules. So whenever we need some kind of a building procedure, we need create some big molecule, then always exclusively we have to rely on covalent bond. So that's the difference. Okay, so with that, probably as long as you can understand, and all this chemical bond discussion would be, I think, it's very satisfactory. Now, we can jump into our main issue, the purpose of looking at 4 major biological macromolecules. They are, once again, carbohydrate, lipid, and proteins. Guess why I put this rainbow color on proteins? And nucleic acid. Nucleic acid is very dull in color, on the other hand. Once again, these are so many different area of inside of a cell's component, many different, each of different 4 major macromolecules are needed. And I'm not sure how many of you can recognize this the meme, because probably when these were in fashion, probably you were not even born, I guess. Were you? Have you remember like seeing in these four guys on TV? Okay, so you are old enough. Maybe you are at the same age as me, maybe. So, my own version of like a comparison of this, each different for major, the macromolecule is this. This guy represents the carbohydrate, I guess. And this guy, on the other, lipids, and protein, and nucleic acid. Why? Guess what? For one reason, this lipid, unlike general convention, lipid is the smallest unit macromolecule. You have only so much unit that you can expand in building up of a lipid. So for this guy, maybe, probably perhaps is appropriate to represent lipid because among four different major macromolecules, perhaps by the unit. Remember, all these macromolecules are built in the same scheme, which is starting from single unit. We call it as a monomer. Single component unit, then to assemble to build huge, now we call it as a polymer. So this is how we generate the macromolecule, starting from monomer, small component, and put together using what? Chemical bond. In particular, what? Covalent bond, right. Particularly, you just use a covalent bond to generate, now is a big polymer. Now we call it as a macromolecule. So, on the such scheme, if you have some kind of limit in generating the kind of dimension of a polymer compared with others, that's what I meant. It's a lipid. You may think lipid it could go all the way up to as large as anybody. No, lipid can only be so much big. Carbohydrates, I don't know, I mean, you have so many different characteristics about carbohydrates, but I just put the rest of this characteristic by default. Hey, you guys. But protein, there is a very good reason why this guy earned the representation of this protein. Why? No, not really. Do you still remember his punchline? Because he's so special. Yes, he claimed that he's so special. Yes, protein is so special. 나는 특별하다. 라고 he always used to say. Yeah, protein is so special in that it's a shape. That's why we heavily rely on many different functions on protein, because it can provide us with so many different unique special shape, specialty. On the other hand, this guy, yeah, you deserve the name tag of nucleic acid. Why? Because you are so boring. This guy is, yeah, nucleic acid is so boring in structure. It's just a simple repeating unit. So these are some four really distinguishable characteristics of the four different types of macromolecules. And here, always that polymer, these macromolecules are polymers. And also, remember this, monomers. So these polymers, in biology, the way polymers are being built is only through assembling each individual monomers. That's it. How? Using this covalent bond formation. So now what you need to do is, in each four different cases, simply distinguish what specific type of monomers are used to assemble these particular polymers under each different categories. And that's all you need to distinguish. Okay? And this particular type of a covalent bond, the good thing about this is all four different macromolecules use the same kind of covalent bond. We call it condensation reaction or dehydration, which is this. Here there is a monomer. Your task is to put these two monomers together. And you're going to use the covalent bond. But among many different types of covalent bond, one particular type of covalent bond that you are going to use is this. Simply draw a line in between, but you get rid of this two part. And what? One each is one water molecule. So that's why it is called, sometimes it's called the dehydration reaction. That means you are taking one water molecule out, or some other cases it's a condensation, same thing. Dehydration or condensation is the same thing, but simply this is one particular type of a covalent bond where at the end of this reaction, one water molecule escapes, and as a result, you are able to form one covalent bond. That's the nature of this dehydration reaction. That's it. And all four same dehydration reactions is applied to each of the four different macromolecule formation. That's good. So we don't have to memorize any unnecessary additional thing. Same thing, showing different way. And how can I get a refund? I changed my mind. I don't want this polymer formation. I want to go back. You go to the store. Hey, I might refund. And do you have a receipt? Yes. And that's it. As long as you have receipt, you will go reverse, which is the reverse reaction of this dehydration is simply what? What is the receipt here? Water molecule. Because when you try to form this dehydration reaction, one water molecule was taken out. So as long as you bring back that water molecule to the counter, then it will get you the refund. Okay, fine. Then you go to the original status, which was a separate thing. So this so-called hydrolysis is the opposite reaction of dehydration. Hydrolysis, think about this origin of the word. Hydrolysis. Hydro, water. By adding the water, you are breaking. It's hydrolysis. So many general chemical reactions are basically the hydrolysis reaction in biology. Okay? So probably you will see or you will hear many other occasions of this same name of a hydrolysis reaction later on, but which is basically same, the reverse reaction of this condensation. So when you try to break this polymer back into individual monomers, what you need to perform is the hydrolysis reaction. So to do so, all you need is bring up the water molecules. Of course, it doesn't mean that you are going to be able to do this spontaneously. You need some enzyme to do so. However, of course, the enzyme presence is a given, but in addition to this enzyme, you need this some water too. So this is basically the diagram explaining the hydrolysis. Same thing. Okay, so we are going so smooth. Good. So everybody is okay. Follow me. Good. Carbohydrate, the first type of macromolecules. The reason why it's called carbohydrate is simply carbon. Carbo and hydrate. So combined word. So it means the molecule having plenty of this carbon, hydrogen, and more importantly, some oxygen too. So basically every molecule, any molecule that contains many carbon and hydrogen as well, and also as many oxygen, is defined as carbohydrate. So if that is the case, would any carbohydrate hydrophobic or hydrophilic? Of course, you saw already answer hydrophilic. Why? Why would any almost all of the carbohydrates are hydrophilic molecule? Why? Why is any carbohydrate hydrophilic? Because of this guy. Whenever you see this guy, you never miss. This guy is going to make trouble. Why? This guy is a sole electron group. So it will try to catch up, take any electrons anywhere, present anywhere. So as a result, it will create some kind of a polarity. If not ion, usually these carbohydrates are not ion. However, just like the case of the hydrogen bond formation, whenever you have so many oxygen, each oxygen molecule will try to influence some distribution of electron. So it will result in some inequality of this ion distribution. So it becomes a little bit polar. So it will be polar. So if any molecule is polar, then it will be hydrophilic. That's it. So you can automatically consider anything. Anytime you consider the carbohydrate, they are going to be hydrophilic. One good thing about hydrophilic is, they are going to be easily dissolved in the water, fine. However, another problem is, if you are hydrophilic, you are going to have a difficulty in one occasion. As a hydrophilic molecule, you have some problem in. Every living thing is based upon the what? Cell. And the outermost cell surface is made of what? Cell membrane. And cell membrane is what? Is cell membrane hydrophilic or hydrophobic? Phobic. It's a lipid based. So you have a big problem. So passing through the cell membrane, it's much better to be hydrophobic. Because hydrophobic molecule, hey, it's me, you remember me, I will just go through. Sure, you can come through. Because they are same kind of molecule. But if hydrophilic molecule, hey, where are you going? Because it cannot pass through this hydrophobic barrier. But due to have so many important molecules, including these carbohydrates are main nutrients, including this and so many other important molecules are all hydrophilic. So you have a big problem. How are we going to make sure the safe transport of those important hydrophilic molecule in and out through the cell membrane? Any idea? Do what? Protein? Transport protein. Right. Yeah, exactly. That's why you need so many different transport proteins on the surface of cell membrane to take care of, because problem is majority of those important material that we need to bring in and also kick out are all hydrophilic molecules, which have difficulty in passing through cell membrane. So that's another very good thing that we need to remember. Having said that, probably I shouldn't go beyond this for today for your poor soul. So I will just stop here, and the rest of this stuff I will continue on next week, but that's actually as important as anything else this message is. So with that in mind, probably we can go through all different types of macromolecules. Then that's actually the important thing. Have a nice weekend.